Hello everyone, I am Wicaksono, and today I would like to present my homework entitled Design of the 6 degree of freedom articulated robot simulation using MatLab. So, uh, 6 degree of freedom robotic arm refers to a robotic arm system with 6 degree of freedom. So here is the picture of the 6 degree of freedom robotic arm. This is the first axis, and this is the second axis, third axis, fourth axis, fifth axis, and the sixth axis. So there are 6 independent ways the arm can move in 3-dimensional space. These degrees of freedom are typically associated with the rotation or movement of joints in the robotic arm. So here is the breakdown of the 6 degrees of freedom. First is translation along the x-axis. This is the ability of the robotic arm to move left or right along the x-axis in 3-dimensional space. And then number 2 is the translation along the y-axis. So the arm can move forward or backward along the y-axis. And then number 3, translation along the z-axis. This degree of freedom allows the arm to move up and down along the z-axis. And then for the fourth one is the rotation around the x-axis. The arm can rotate around its own axis, known as the roll axis. And then number 5 is pitch, rotation around the y-axis. This is the ability of the arm to tilt or move up and down around the y-axis. And the last is yaw, rotation around the z-axis. So here the arm can rotate left or right around the z-axis. So here each joint in the robotic arm contributes to one or more of this degree of freedom. So the design and control of a 6 degree of freedom robotic arm involve consideration of kinematics, dynamic, and control algorithms to enable precise and coordinated movements in each workspace. Next slide, we will talk about Denavit-Hartenberg parameters. So the Denavit-Hartenberg parameters consist of 4 parameters for each joint. First parameter is AI, the length of the link between ITH and I+1TH joints measured along the common normal, known as the link length. And number 2 is alpha 1. This is the twist angle between ITH and I+1TH joints, measures about the common normal. It is the angle of rotation from ZI axis to the ZI+1 axis about XI axis. And the third parameter is DI. This is the offset along the common normal between ITH and I+1TH joints. So it is measured along the z-axis. Here it represents the distance between the ZI and ZI+1 axis. And then the last parameter is theta I, the angle of rotation of the ITH joint about the ZI axis to align the XI-1 and ZI axis. So here, the Denavit-Hartenberg parameters are a set of 4 parameters associated with each joint in a robotic arm, providing a systematic method for describing geometry and motion of the robot's links. So next we can continue to the MatLab. So next we can go to the MatLab for simulation. First of all, we have to install the RVC toolbox. Then after we finish with the installation, make sure that here we put the path of our RVC tools installations here. And then we can continue to run the RVC tools. We can type here startup underscore RVC. After that, we can continue to check the models that we have by typing the models. Here are the models of our robotic arm that we can use to simulate the movement of our robotic arm. So here I will use the 6 degree of freedom robotic arm here. There are some 6 degree of freedom robotic arm, and I will use the universal robotic UR5 6 degree of freedom standard edge. We can type MDL underscore UR5 to use this robotic arm. MDL underscore UR5. Then after that, we can check in the open variable here what kind of variable that we can use to run the simulation in using the universal robotic UR5. Here the variable is UR5, so we can type here UR5 dot teach to run the simulation. So here we have X position, Y position, Z position, and then this is a roll angle, pitch angle, and also yaw angle here. And this is the Q1 until Q6 represent the joint on every link that we use in the 6 degree of freedom robotic arm. This is the joint 1. We can slide the bar here to move the first joint of our robotic arm. And then we can also use Q2 to move the joint number 2 and Q3 to simulate the movement of third joint, Q4 for the fourth joint, Q5 for the fifth joint, and then Q6 the sixth joint. So in the assignment, we have to make that the roll angle here is about 30 degrees, and then the pitch angle here is about 60 degrees, and the yaw angle is about 90 degrees. So we can make this all joint in the normal position. We can put 0 to all angle here. Okay, since the yaw angle is already 90, so we do not need to adjust this angle. We just need to adjust the roll angle and also pitch angle here. We can modify the Q1 parameter here to adjust the pitch angle in 30 degree, and then for the Q2 we can use it to adjust the roll angle in this is the pitch angle should be 60 degree, and then for the roll angle 30 degree. So here our setup: roll angle 30 degree, pitch angle 60 degree, and yaw angle 90 degree. So this is the end of the presentation. Thank you for your kind attention.